Many physicists are searching for a toe, a theory of everything. You often hear, it's not science if it's not mathematical. Could you comment on that?
Sure, I'd be glad to. First of all, the physicists who are searching for a toe are probably only looking for a little toe. They're not looking for a big toe. They don't even know a big toe exists. They're looking for a way to find something that will derive both relativity and quantum physics. Because right now, quantum physics and relativity have some inconsistencies, some logical inconsistencies between them. They don't mesh together very well. And they're looking for an overarching theory that will derive both of those with one understanding. So that's a little toe. That's what Einstein was looking for. I don't think there's probably very many physicists who realize there is such a thing as a big toe, which is a theory of everything objective and everything subjective, both worlds. In other words, it takes in consciousness. It's also a theory of consciousness, as well as a theory of the what we call the physical world. It's both of those. That's what I call a big toe. Now, about the mathematical business, looking for something fundamental in physics, looking for something that is a major paradigm change. They need to not be looking for things mathematical. They need to be looking for things that are logical. You see, science does not run on math. Now, they think it does. They think the engine of science only runs on math, but it doesn't. The engine of science runs on logic. If it's logical, then it's important. It's factual, logic and facts. That's what science runs on. And math is logical, but it's just the narrow case of logic where math is at least the kind of applied math that physicists use. It's the logic of quantity. Well, that's good logic because most of our world has to do with quantities, how big, how much, it's all about measurement, and measurement measures quantities. So the logic of quantity is going to be very useful in describing physical reality, but it's not the only thing. You see, all big paradigm shifts start with big ideas. They don't start with a lot of math, because at the fundamental level, science is logic that's really beyond math. When it gets down to the details, the logical consequences of the big ideas, now mathematics becomes a very good tool. So I'm going to talk about that in a video that we're going to do very shortly. And besides that, I'm going to make this a trilogy of videos, if you will. The first one's going to talk about kind of the fundamentals of science. What is science? What does math have to do with science? How does MBT fit into science? What's MBT? What is MBT's claim as far as where it fits into science? How does it fit into science? And why is there an absence of math in MBT, which is the way it should be? Okay, so I'd like to talk to all of that, and that will be the first part. The second part is going to be not the logic of science, but rather the logic of virtual reality. I'm going to introduce virtual reality, and we're going to look at some of the consequences of that logic. So that will be part two. And that will kind of define the landscape of what this science that MBT has developed. It'll be kind of the logical framework that MBT is hanging on, is what it'll be. And then after that, I'm going to have a third part, which is going to be showing examples of exactly how this logic solves physics problems, solves science problems. In other words, first we talk about the general philosophy of science, math, and MBT, and get the proper perspective of how MBT fits in. Secondly, we're going to talk about the logical structure in which MBT is cast. And then thirdly, we're going to take that structure and actually solve some physics problems with it. I'm going to explain to people the mystery or the paradox of Schrodinger's cat. And what that means is that I'm going to explain it logically. You see, physicists will explain Schrodinger's cat, but they'll say things like, the cat is in a superimposed state of being both dead and alive at the same time. Or maybe they skip the superimposed states. They'll just say the cat is both dead and alive at the same time. And of course, when they say things like that, what they're doing is they're looking at the math and trying to interpret something physical from the math, some physical process from the math. And that's what they're saying has happened. So that's why they end up saying really silly things like the cat is both dead and alive at the same time. Of course, anybody knows that's impossible. The cat is not both dead and alive at the same time. The cat is not in a superposition of, those two states, dead and alive. That's the problem physicists get into when they believe that their math actually represents physical reality. Their math does represent reality, but not necessarily physical reality, you see? So that's how they run aground and end up saying foolish things like the cat's both dead and alive at the same time. It's not. So I'm going to go through it, and I'm going to show people exactly how the system computes whether the cat is dead or alive. And we'll see that process. And guaranteed, nowhere in that process do we need a wave function. Nowhere in that process do we need a superposition of dead and alive cats. All of that is just nonsense. But it's the kind of nonsense you get when you look at the math and try to interpret that math in physical terms, you see. But that math is not explaining something that happens in physical terms. This is a virtual reality. So the second thing I'll do in that third part is explain the double slit experiment. And I'll do the same thing. I will lead the reader through the double slit experiment so they can see exactly how the rendering engine that renders this virtual reality comes up with the answers it does. So why is it that when the observer looks at what slit it goes through, you get a particle pattern, and when you don't, you get an interference pattern? Why is that? Well, quantum physics would tell you nobody knows, nobody will ever know. It's just weird science, the old shut up and calculate thing. Well, that's not the case. There'll be no wave functions. It won't be that it's, that there's probability that the particle could be found anywhere, and we sum up all those probabilities. That's kind of the idea that Feynman had, but it doesn't really work like that either. It's a simpler, easier thing. And you don't have to shut up and calculate. All you have to do is understand the logic, and you can see what the right answer is going to be without doing any math at all, just by following the logic. So that's going to be this trilogy of YouTube videos that I'm going to do. We're going to do the first, it's going to be science, math, and my big toe. And the second is going to be and that's really the logic of science, is really what we'll be talking about. And the nature of big discovery, the nature of paradigm shifting discovery. And the second one is then going to go over the virtual reality, its logic, what it tells us. If we follow that logic of virtual reality, the idea is if this is a virtual reality, then, and now what I will do in that one is answer what comes after then. If it's a virtual reality, what does that logically imply? And there's a lot of very interesting logical implications there. And lastly, the examples. How does it work? How does this logic of virtual reality actually produce the answers to physics problems? We'll solve those two. And I actually have a little a spreadsheet I have with Schrodinger's cat to actually do the calculations that the system would do. And you can just see this is how the system does it. And you will see exactly what the process is. And you will see that this process is actually described by quantum physics math, but it's not the way they interpret it, because they're trying to interpret it to be a physical process. This is a virtual reality rendering engine process. So that's what's coming. It's going to be all about science, all about math, all about Schrodinger's cat and the double slit experiment. So all of you viewers, it's coming up, and everything you needed to know about the science, my big toe, virtual reality, and actually what happens to Schrodinger's cat, then tune in and all that will be coming.
Well, thanks, Tom. That sounds really fun. Let's get started.
Okay,
All right.
we will.
Good afternoon, Tom. Thank you for being here today. Some scientists have reservations about your big theory of everything because it's not math-based. Is that something you can comment on?
Well, sure. You know, I've heard things like that before. Many years ago, long before I wrote anything down on paper to make books, the idea was that if Einstein had just talked about, you know, his theory of relativity, but didn't have any math, nobody would have listened to him. Wouldn't have made any difference. You know, it's like science can't digest it or understand it or whatever if it's not in terms of mathematics. Mathematics is the language of science. So if it's not math-based, then it's not really science. And I've heard that, and probably when I was a young physicist, probably even believed it, but that's a small view. It's partially true in some cases, but it's not the general view. Now, what is true and necessary is that the theory be logical. See, that's important. If it's not a logical theory, then it can't be science. Now, mathematics is just the logic of quantity. That's all mathematics is. You know, mathematics is, 1 + 1 = 2. It's the logic of quantity. Indeed, the way computers work is they do their multiplication. Multiplication is just a shorthand for addition, right? It's really addition. And the same with powers. You raise things to powers, that can all be reduced to addition. And if you look at the way computers work, they're just really, really fast adding machines. They reduce most of these functions into addition. Okay, so it's just the logic of quantity. That's fundamentally what math is. Now, math is a big subject, so I should, the applied math that's applied to the world, to physics, that is the logic of quantity. There are other kinds of math that are not necessarily just the logic of quantity. So I shouldn't say that about math as a collective whole, but rather about the applied math that's applied to represent the physical world, like the math that physicists use or applied mathematicians use. That's the logic of quantity, and that is a logic. So if something's math-based, then it is logic-based according to the logic of quantity. But that's not the only thing that matters. Quantity is important because almost everything in our physical world is described in terms of quantity. How much of this, how much does that weigh? How tall is this? How broad is that? How deep? Obviously, all the dimensions are quantity, but how many atoms, how many molecules? I mean, it's all about quantity. That's how we describe our environment in terms of how much of what we see. Well, so math is a good, the math of the logic of quantity is a good mathematics to use for describing the natural world. And it seems to apply, but it's not exclusive. There's other logic that is also important. And it's not true that if it's not mathematical, it's not science. That's not true at all. If it's not logical, it's not science. That's true. Okay, but math is just one kind of logic. So let's look at the big paradigm shifts that we humanity have gone through, really big paradigm shifts. And we will see that most of those really big paradigm shifts, and I mean the things that change the way we see the world, change the way we see reality, big differences in how we see ourselves in the world and how we see the world. These things in general do not start out mathematically. They are ideas, they're concepts, but they're logical. So let's start out with, I'll try to maybe do them in order. We could do things like, the invention of the wheel and the domestication of fire. That might be hard to call that science, but it is, in their time. And all of these were not obviously mathematical, but they had huge impacts on humanity. Okay, they were ideas. They were logical, though. So it's just logical. How do you domesticate fire? Well, you have to contain the heat. How you get a wheel to go round and round? Well, it's something whose surface never ends. It just goes round and round and round. You say you don't have to move it or lift it or do something to it. It's logical. So logical things can make huge differences to humans. And get really to something's more scientific. Look at the idea that the Earth was the center of the universe. Well, that made some sense because it looked like from an Earth viewpoint that the sun went around the Earth. It'd go from east and across, and go to west and come back up in the east. And it just seemed like its sun went around the Earth. And it seemed like the moon went around the Earth. It seemed like all the stars went around the Earth. It made sense that the Earth was the center of the universe. That was a belief. And then there was, the idea that the Earth wasn't the center of the universe. And suddenly it's like, well, that's not reasonable. We can just go out of our window and look at day and night, and we can see the things going around the Earth. But there was other things that were not explainable in our sense of the cosmos. Why did we have 4 seasons? Why do we go from cold to warm and go through, fall and spring in between? What about the day? What about day and night? How does that happen? It's just because the sun, I guess, travels around the Earth, and it makes part of it day and then part of it night as it goes around the Earth. So we have seasons, we have day night, we have the stars, and all of this motion relative to each other was worked on by scientists and mathematicians trying to figure it out. And they had very complicated math called epicycles that computed all the heavenly bodies, the things that were out there, according to the Earth being at the center. And you can do that. There's nothing fundamentally wrong with the Earth being the center of the universe. It just makes all the math very difficult. It makes understanding very difficult. Everything becomes more complicated if you take that viewpoint. It's just not a natural viewpoint because of the way things are laid out. So then we got to the sun being the center of a solar system. Okay, so now suddenly a lot of things made sense. You get day and night because the Earth rotates on its axis. You get seasons because its axis is tilted a little bit, and the Earth goes around the sun. different ideas altogether. But suddenly we explained things that were mysterious before. We explained, the day, not only the day night, but the seasons as well. Okay. And we could see how the stars were different than those. So the stars weren't part of our solar system. And we could see how they would look like they went around the Earth too, because the Earth was rotating. You see, it was just a different model. It's like, just let's look at it from a different perspective. And if we find a different perspective that simplifies our understanding, improves our understanding, then that's good. That's a new model. So let's say the old model was the Earth is at the center of the universe. Okay. Nothing fundamentally wrong with that, other than that model is hugely complex and it doesn't account for a lot of things. Still a lot of mystery and a lot of paradoxes. So we get something simpler that says the Earth is rotating around the sun. The sun is the center just of our solar system, not of the universe. And now suddenly we've got weather, we've got we've got tides, we've got not only day and night but seasons. So we understand things a lot more. Okay, now the idea, once we have that concept, there's really no math there. That's just a concept. And then people, once they have that idea and see how that works, and if you look back in the, I don't know when this started, 1700s, you see they had these models, and there was a big crank that you turned, and when you turned that crank, the Earth went around and the moon went around the Earth, and they had these, I don't know what they were called, but they basically were like the first planetarium sort of thing, where people could visualize how the heavenly bodies moved. And there were big mechanical things with gears and cranks and so on. And that's where the ideas came from, okay, because people could explain things with those ideas. Then we look at that and say, well, why should the Earth go around the sun? And why should that happen? And then we start to see the math show up. Oh, look, that's an ellipse. Or maybe we first thought it was a circle. And then we found out that, well, that's not quite right. That doesn't quite fit the data. It's an ellipse. Well, we could come up with the math for an ellipse. Now, why would they do that? Well, then we come up with the concept of gravity. There's a force making that happen, because when we spin a ball around on a string, we can feel that force. So now we come up with the concept of gravity, you see. So we can develop theories. And as we look at the logical consequences of a theory, like a theory that the Earth goes around the sun and that the Earth is on a tilted axis, when we look at the consequences of that, the logical consequences, now we can start applying the math to describe the details of what we see. But we first start with a logical concept, something that explains what we see. Not necessarily a lot of detail, not necessarily a lot of math, but the concept has to come first. Science doesn't work by, some mathematician one day coming right out of the blue without having any idea of celestial systems and just pronouncing that, the Earth goes around the sun with an ellipse. You see, it doesn't work that way. It works first with the concept, first with the understanding. Then the math comes along to explain the details better, because it answers the why. Why could it work that way? How does it work that way? So starting with the concept that the sun was the center of our solar system, we ended up with things like gravity. And because we know that had to be an inverse force, because we could do that in our own little labs and see that there was a force there, we could feel it on the string. So Newton comes up with this little inverse square relationship, that the force of gravity is inversely proportional to the square of the distance between things. Aha! So we're starting getting math, but math is fleshing out what was first logical conception. You don't start with math, you start with logical conception. Then the math fills it in as that logical conception, needs the math, so to speak, to fill out the details. So that's the way it works. So yes, a theory must be logical. If it's science, it must be logical. But math comes later to work out the details. Okay, so let's, what was the next big thing? Oh, well, the Earth being flat, I guess that fits right in there too. If we are a sphere going around the sun with gravity, then obviously this flat thing didn't work out very well. And that was another big idea. But somebody didn't sit down and say, oh, look, the math shows that the Earth is spherical. That didn't come first. They saw that ships, when they went out from dock, looked like they were sinking in the water. First you'd see the whole ship and then just the top half and then just the top of the mast, and it would disappear. And it was like they were going out and sinking. Well, they were traveling around the surface of a sphere. They were going below the line of sight. And you look at the moon, and the shadow of the Earth on the moon is a curved shape. Okay, so they had evidence like that were paradoxes, and the Earth being spherical kind of fit those paradoxes. And that was known 200 years before, Columbus sailed the ocean blue. It was 200 years before that people understood that the Earth was spherical and not flat. Today, it's coming back up in a question again, But in any case, okay, it's the same thing. The idea is that first, you have the concepts and the understanding from the things that you can see. That's logic. Look at the curve of the shadow on the moon. Look at the way the ships sink down into the water as they go away from the dock. This is data, and you can use logic to come up with a model. Then eventually, the mathematics gets to work out the logical details of that model more precisely as we look at the logic of quantity, like exactly how fast does it spin and how long does it take it to go around and other things. Well, now you start to need math to work out the details of the quantity of the concept, you see. So the big ideas that have changed things don't start mathematically. You have other big ideas. The Iron Age changed everything, right? When suddenly metallurgy became a science. Well, it didn't start with math. That started with logic. People saw that this stuff melted, and then when it got cool, it held its shape. Oh, what could we do with that? It was just logic. Wow, made a huge difference to humanity. You see? Again, it starts as logic, and then in the end, and then later on, you apply the logic of quantity to sort out the details. So all the big ideas that have changed humanity and changed our reality, changed the way and how we are, work out that way. The Industrial Revolution changed everything. We're not at all like we would have been had we never gone through an industrial revolution, but that didn't start out with math. So you may be thinking that, well, these things aren't science, but that's not true. There's a lot of science and engineering went into that industrial revolution. People made machines. I mean, it was engineering, but also a lot of science was done. Those are maybe just the early days of science. So we can move on forward to the computers and the information age and look at that. Well, that again started out as concepts. It was conceptual. And as we get further down that line, we get more and more into the details, more and more into working out all the tiny little logical trails, logical possibilities, what we can do. And that's, as we find new logical possibilities, we have new inventions, new ways of figuring things out. And then we use the math to explain them. So the math isn't necessary for science. Good ideas, logic, concepts, understanding, looking for patterns, looking for things that fit, figuring out how to explain paradoxes, coming up with models that explain things that are now unexplained, like why do we have the seasons? Things like that. That's science. Science is using logic to investigate the natural world, to investigate our reality. That's what science is. It's a logic-based thing. And of course, we use math too, because that's the narrow logic of quantity, not logic in general. And because our reality is measured mostly in terms of quantity, it fits very well, particularly at the details. But math generally doesn't do much to come up with the big ideas, you see. So just because something is not math-based probably means that either the science is not that complex or that it's still in a conceptual phase. But that's where we start, is with the conceptual phase. The logical consequences will work themselves out later. They don't come first. They have to dribble along after the concepts become more understood and more widely envisioned. Then we start getting math applied to, well, what else does that imply? You see? Okay, so that's kind of the relationship, with logic, math, and science. But there's a couple of other things worth talking about here, and that is that scientists, physicists in particular, often confuse themselves with math because they don't really take a lot of time to learn about the philosophy of science. So they don't have a big picture on science. The philosophy of science kind of gives you the big picture. So they describe something mathematically, and they see that what they describe tends to fit what's in reality. Then they try to how can I say, interpret the math with a physical interpretation. Oh, you see, they'll say, well, okay, this works. Well, quantum mechanics is a really good example of that. All right, they used Schrodinger's wave equation. They said there's a wave. It's a probability wave, nothing physical here. We're not talking about physical waves. We're talking about probability waves. And they compute something, okay? And they get the right answer. Okay, quantum mechanics is a good science. But now they take that wave function and that mathematics, and they try to make a physical interpretation of it. They try to say, what does this mean? What does this math mean? How can I interpret this math physically? Okay. Now, sometimes they can come up with some decent ideas about that if the problem's simple, but with quantum mechanics, the problem wasn't that simple, you see? So then they do the double slit experiment, and they find that one particle, if you do not look at which slit it goes through, rearranges itself in some interference pattern on the screen. Well, how does that happen? And they look at their math and they say things that are really foolish, things that are really kind of silly that no real scientist ought to say. But you'll hear physicists saying those things like, well, it looks like the particle must go through both slits at the same time and interfere with itself. Huh? No, particle doesn't go through both slits at the same time. It's a particle, and it doesn't interfere with itself. That doesn't make any sense. But they'll say things like that. They'll look at Schrodinger's cat and they'll say, well, the cat is in a superposition of both dead and alive. And when we make the measurement, then we get a result, dead or alive. Well, that a cat is in a superposition of dead and alive also doesn't make any sense. That's a struggle where people are trying to give some kind of physical interpretation to the math. Okay, now the math is right. I'm not faulting the math. The math is correct. And those things do happen. But it's not because the cat is both dead and alive, and it's not because that the particle goes through both slits and interferes with itself. Those are just, I don't know, what can I say? People making things up because they don't know what else to say. And that's sort of what the math looks like is going on. So they actually believe that that somehow is happening, that the cat really is existing in two superposition states, and the cat is both dead and alive. You can't be both dead and alive. You're either dead or you're alive. Being both dead and alive is not a real thing, you see. So the math can lead physicists to make statements that are silly. And they just confuse themselves with these silly statements. Oh, well, of course the cat's both dead and alive. See, that's what the math says. No, that's your interpretation of what the math says. Now, if you took philosophy of science, you would realize that whenever you make a physical interpretation of an equation, that you're really making things up. That's not a fixed thing. That's, well, this is how it looks to me, kind of a thing. That is somebody coming up with something. That's called, what is it? You reach up and out of the clear blue sky and pull something down. That's conjecture. Whenever anybody gives physical significance to equations, that's conjecture. Now, that conjecture may be really close to being true if the situation's very simple, but as it gets more and more complicated, that conjecture tends to get further and further from the actual truth. And we say things like, well, you know, the cat's both dead and alive at the same time, and we pretend that that somehow makes sense. And scientists say that with a straight face, but obviously that's just not true. That's not how things work. The cat is not both dead and alive at the same time. The real answer is there is no cat. You see, that's the answer, is there is no cat. This is a virtual reality. Okay, it's a virtual cat, just like, you know, my body, Tom Campbell's body here is a virtual body. And once you see it from that perspective, then things suddenly simplify, just like they did when suddenly the sun was the center of our solar system. And our sun was just one among millions of suns in our galaxy, or even billions of suns in our galaxy. And our galaxy is just one in, you know, a very large number of galaxies, and the galaxies form super galaxies, and so on up, you know, the structure goes. So in any case, my point is math is nifty, and math is the logic of quantity, and it does us a lot of good in science because most of the physical world is in terms of quantity. But as soon as we talk about this being a virtual reality, we're not in that physical world anymore. All that physical world stuff doesn't really apply here. This is a virtual reality, you see. So you have to think a little differently. And when you understand, you know, how the reality actually works, and for those of you who would like to go to more detail, go see my talk back in 2016 called MBT LA-2016. So it's a talk I gave in Los Angeles in 2016, and it'll have the details, and it'll show you, you know, how that actually works and how the Schrodinger cat actually works. You see, from the viewpoint of virtual reality, from that perspective, something that is now very complex and hard to understand, like a cat being both dead and alive at the same time. Wow, that stretches your brain, doesn't it? You know, all the stuff that seems so complex falls out very simply. There's a very simple logical description and explanation of how that works. how the particle ends up in an interference distribution on the screen when it's only one particle at a time going through the slits. Makes perfectly logical sense from the perspective of virtual reality. It couldn't be any other way, you see. So yes, math is generally a part of science, particularly more mature science. Science that's been around, the concepts have been around for a long time. The longer they've been around, the more people have explored the logical rabbit holes of how much, the ideas of quantity. That's what I'm trying to think of. The more they explore the relationships of quantity to each other. So my big toe is conceptual at this point. Seeing reality as virtual and not a physical thing solves hundreds of paradoxes. It makes quantum mechanics not a weird science, but a logical science. And no, you don't have to do the math to see what the result of the quantum mechanics is going to be. All you have to do is follow the logic. You can set up your diagram and say, here's the logic and here's going to be the result. You don't have to do the math like, what was it? Feynman said, shut up and calculate. You don't have to do that. All you have to do is follow the logic, which makes sense. Every other science is a logical science. All of it, every science is a logical science. You can see the logic behind what's going on, except quantum mechanics, and that's a weird science. You can't see it. You got cats that are both dead and alive at the same time. You've got particles that go through both slits at the same time, a single particle, and then interfere with themselves. How weird is that? It's just weird science, ladies and gentlemen. Well, it's not weird science. It's only weird science when you take the wrong perspective. And that's the perspective of materialism. When you have the perspective of materialism, that this is a material world, then quantum mechanics just doesn't make any sense because the perspective is wrong, not because the science is weird. It just looks weird because the perspective is wrong. From the perspective of virtual reality, the weirdness all goes away. You see? So, and I'm going to do a little video here with you in the near future, talking about exactly how that double slit works, why it works, the logic of it, and Schrodinger's cat. We'll look at the logic of that too. And you see that it does not require wave functions, and it does not require that the cat's both dead and alive at the same time, or that a particle splits in two and interferes with itself, or that its probability wave interferes with itself. None of that is necessary. You don't need wave functions. Matter of fact, back when quantum mechanics was first being generated, there were two alternative ways to get the right answer. One was Schrodinger's wave equation, and the other one was Heisenberg's matrix model. They both worked. They both got the same answer. But one had wave equations, the other one didn't. So a wave equation is not necessary. It's just a way of looking at it. It's just a model. It's a model that somebody made up to get the right answer. And that's good. It does get the right answer, but the problem is it doesn't know why. It doesn't know why it's getting the right answer. It doesn't understand the fundamentals. It doesn't understand why should particles really be probability distributions. When you have a virtual reality, you can answer that question. Well, they have to be probability distributions. That's the way the virtual reality is made. All particles are probability distributions. So is everything else. Comes out of probability distributions. It's the nature of the virtual reality. Okay, now not any virtual reality, but it's the nature of our virtual reality. Okay, so my big toe is in the conceptual phase. We're talking about big ideas. And once people see how all these paradoxes are solved just by this one change in perspective, paradoxes in biology, paradoxes in across the board in neuroscience, paradoxes everywhere, a lot of them in physics. Once they see how that it does that, it's just like seeing, oh, look, we got the seasons, we got the day and night, we've got, so many more answers about what's going on, the way the stars move relative to us. And wow, whole bunch of paradoxes all got solved just with that one change in perspective to a better perspective that allows you to understand things more easily. It's not that the Earth is the center of the universe is wrong. You can do the math from the Earth being the center of the universe, and you can calculate everything we calculate now. It's just a matter of shifting the origin in your vector analysis. You shift the origin to the Earth instead of the sun for our solar system, or the center of our galaxy for that. So it's not that one is fundamentally truer than the other. It's just one is a better model than the other. The model with the Earth at the center of the universe is all kinds of complex mathematics to explain everything. The one with the sun at the center, oh, that falls out neatly. And hey, we get gravitation to boot with that one. We have a nice gravitational model that sits right at the center of it. So it's a much better model. And now that we talk about gravitation, we can talk about that too. With Newton, the model of gravitation was that masses attract, and they attract proportional to, again, an inverse square law. They attract each other. Now, there was no explanation of why they should attract each other. Well, that was unknown. They just did for some unknown reason. It was one of those paradoxes. Einstein made a different model. And his model was that you had space-time, and space-time got warped, got stretched as you had masses there, bigger masses. They'd stretch it, and they got the model of put the bowling ball on the trampoline, and you'll see it makes an indentation, and that other things around it will roll in towards it because of that change in space-time. So that's another model. Is Newton wrong and Einstein right? No, they're just two different models of the same thing, such as the Earth being the center, or the Earth, or the sun being the center. Two different models, two different ways of looking at it. And the model that Einstein came up with is more general, allows us to compute more things that we couldn't compute with Newton's model. So then we say, well, Einstein's got the better model. It's more complex, it's more complicated, but it does more. It does relativistic artifacts in gravitation. Okay, but still, you see, there's a lot of unknowns. Okay, now if Einstein had no mathematics and he just said, I think space-time stretches, and you put mass in it, and mass kind of stretches space-time, and that's why we have things, that's why masses look like that they're attracting each other. They're just rolling downhill toward each other. The little ones roll down toward the big ones. That's the way it works. He could have given that model that way, and it probably wouldn't have meant so much, because they were down now, not in the very conceptual viewpoint. And I'm sure Einstein had that concept before he actually turned it into mathematics, because again, the concept has to come first. You don't lead with mathematics, you lead with concepts. And he probably had that concept of that being a solution. And then he did the mathematics to support it. And it turned out it was a good model, a better model, particularly if you have to deal with things that are traveling very fast over large distances. It's a better model. So in that case, Einstein may or may not have gotten very far if he just had the idea, okay, because we already had a model for gravitation that worked pretty well. He needed to have more than just the idea. He needed to have the math with it. So that was kind of at a later stage of gravitation, you see. So we have to look at things that are basic, new big paradigm shifts. Okay, now for Einstein, actually his not general relativity, but his special relativity was really where the big paradigm shift started. That was the length contraction, the masses increase, and so on. We had all the time dilation. We had all these very strange things going on, and those strange things went on for one reason, and that was the speed of light is always a constant. No matter how its source is moving, the speed of light is always a constant. That's the thing that made those weird things like time dilation and length contraction and mass growing as the speed went up, as the speed approached c. So that's where the big conceptual things were. And after that, it was working out the details in a different way, in a geometric model, as opposed to the old idea that masses attract each other. Now let's look at another big paradigm shift, and that was Darwin's theory of evolution. Big paradigm shift. Okay, now we talk about evolutionary science and biology as a science, and it explains so many things. So many things could be explained with this theory of evolution that before were just paradoxical. No idea why it was like that, you see, but Darwin didn't start with a lot of mathematics. He started with an idea. But now look at biologists today. Okay, look at where they have taken Darwin's theory, the details that they now understand, and you will find that the evolutionary biologists, you do a lot of math. That's science, okay? Because they've gotten to the point they're down in the details. They're measuring, they're computing and calculating. Well, yes, but the idea didn't fall out of the math. Right. The math comes after the idea. So you see, that's the difference. Yeah. So we look at these big things, flat Earth, Earth, the center of the universe, evolution, big paradigm changers. We thought about everything afterwards differently. They all start as big ideas that answer questions, that resolve paradoxes. And math, to look at that and say, well, Darwin, where's your mathematics? That's not science. Why don't you and your beagle just go sail off the edge of the earth, right? We can't look at that because there's no math involved. Math is not appropriate at that point. First comes the concepts.
Would you say, Tom, that your conceptual theory that we live in a virtual reality is logically derived? I know you stated that, but that the equations and the math that scientists are demanding are just a subset of this.
Oh, sure.
Logic.
It's just a subset. You see, what my model does is it provides the fundamentals that are the foundation really underneath the math. The math doesn't make the foundation. The foundations is how the world works. It's the basic functioning of our reality, how that works. That's the foundation. And the math describes it. It approximately describes it. It doesn't actually describe it exactly. It just approximately describes it. Okay. So you start with logic. It had to, what Darwin did was logical. He looked at all the evidence, made logical inferences from that evidence. So he formed the foundation upon which modern evolutionary biology could exist. You say, well, now here we are in physics, and we've got these unknowns. Why does light always go at the same speed? If a light source is moving, shouldn't the light go, its own speed plus whatever the speed is of its source? No, it always goes c. Well, why is that? Well, the virtual reality viewpoint explains that very simply. And quantum mechanics, again, why should particles be probability distributions? Well, probability distributions are their natural state in the virtual reality. That's what they are. They are probability distributions, and they can't be anything else. That's the way this particular virtual reality works. It's a probabilistic virtual reality. It's not one built from the ground up. On physics, it's built, from the top down in probability. And there's a reasons why that has to be so, that it can't be any other way. It's not, you don't start at elementary particles and build up atoms and build up molecules and then make a virtual reality that way. That's foolish. That's way too computational intensive, and it is completely unnecessary. There's better ways to solve that problem, and they involve probability and statistics. So in any case, what my model does is provide the foundation that is underneath the math that you get downstream. So understanding why C is a constant and why particles are probability distributions at a fundamental level then enables you to do quantum mechanics and come up with a wave function and understand why that's the case. It's not weird science. It's just telling it the way it is, you see, and then the math follows. So there's lots of these paradoxes. Matter of fact, even physics itself is based on a bunch of paradoxes. I mean, talk about science. Science is supposed to, be causal, right? Everything has its cause. Science is based on a few basic things: space, time, gravity, charge, spin. I don't know, there may be a couple of more that come to mind, but these are the fundamental things. And all the rest of physics is made up of how these things relate to each other, pretty much, all the way that they can interact with each other. If you let space and time interact, you end up with speed and velocity and, things like that. So it's the very basic things, but look at all those basic things in physics. Where does time come from? Who makes time? What's the cause of time? What's the cause of space? What's the cause of charge? Where does charge come from? You see, all of these things that are basic, science has no idea. They have no cause. And you ask a scientist, well, where does this stuff come from? Where's its cause? And they'll say, it just is. Well, if I told you that something just is and didn't have any cause, you'd call me a lunatic, So, well, that's crazy. What do you mean it just is? What kind of answer is that? It just is. That doesn't sound like science. That sounds like hocus pocus. Oh, the rabbit comes out of the hat. It just is. How'd that rabbit get in the hat? Well, it just did. No explanation. Well, when you look at virtual reality, you'll find a solid explanation for all of those things, for where they come from. How'd they get there? We have this with the anthropic principle or something like that, that physicists have come up with, that there's some fundamental constants. We can even call them constants of the universe that allow this universe to exist. It's a very, very fine-tuned machine. And if any of these constants, like gravitational constants, one of them, if any of these constants were just changed a little, even in the 10th decimal place, the whole thing would collapse. It wouldn't be stable. So we have all these constants. Well, how did all those constants get just like that? I mean, to 10 decimal places, really? How did that happen? That sounds like it was designed just so it would work, just to be stable. It's like, is that the intelligent design that people talk about? Well, if you come at it from a virtual reality viewpoint, you'll find exactly how that works and where they came from and how they got to be that way. Those numbers evolved to be what they are. Cut and dry. They evolved. They had to be what they were to make the whole thing balance and work. You see, so And what's the process for that? Well, again, you understand where it comes from. The Big Bang, where did that ball of plasma come from that made this universe? It just came out of nothing. We start with a ball of plasma, high temperature, high pressure, and boom, we have a Big Bang. And now we have a universe that can evolve from that. Yeah, but where did that ball of plasma come from? Oh, I don't know. That's another paradox. And from the virtual reality viewpoint, it's explained logically. So that's the key. Once you have a new perspective that explains things better than the old perspective, then you have an effective model. And if it doesn't mess anything up, it has to explain, all the paradoxes, but it has to also explain all the things you also know, like the wave function. Yeah, that wave function is a good way to express the probability that's inherent in the virtual reality model. You see, so what my model does is it builds a foundation under physics. Physics now starts from a very shaky foundation of, well, I don't know, they just do. They just exist. They came out of nowhere. They just are because they are. Well, that's really a crappy foundation for a science. And my model then explains, where do they come from? Why are they there? How did they get to be that way? You see? So that's kind of the bigger picture. So why isn't my model basically mathematics? Well, we haven't gotten to that point yet. It will spawn mathematics. Matter of fact, the idea of a process fractal is kind of a new mathematics that I introduced in my model. Well, it's a whole new concept. We have geometric fractals, but there are also process fractals. Evolution is a process fractal. And once you see that as a process fractal and not just, something happened and it just kept going, you get to see the pattern, and you see there's other process fractals that have to do with our sociology, how we interact, our environment, our ecology, all of that you can see in terms of process fractals. So it's not time yet for MBT to be covered over with math. This is the conceptual, foundational phase. And physics has a saying in it that basically it's called Occam's razor, that says if it's foundational, it's simple and it's elegant. If it's not foundational, it can be very, very complex and very complicated. But if it's foundational, it needs to be simple and elegant. And that indeed is the way virtual reality model works. It's simple, just a couple of simple ideas, and bingo, all of these paradoxes have solutions, have answers. So that's where we are. And things that are simple and elegant are not described by pages of mathematics. Things that are simple and elegant can be understood by everybody, can be spoken about, can be described in language. They don't have to have a lot of complex math. Matter of fact, Albert Einstein left us a quote where he said that he had an aunt or a niece, or it was some lady to whom he was related, and he made the statement that if he couldn't explain it to her, then he realized he didn't really understand it that well himself. Because once you really do understand what's going on, then you can reduce it to something that is the foundation of that thing, the very foundation. But a lot of our science now has no foundation. It kind of starts in the middle and goes on. It's wanting a foundation. So we've got weird science. We've got relativity that's based on C being a constant and nobody knows why. So we kind of started in the middle and we're chugging out the math like crazy. And we think the math is the science. The math isn't the science. The understanding's the science. The math just helps us describe what we see. The math doesn't generate what we see. You see, the math just, action at a distance. You have action at a distance, electromagnetic fields, and so on. These are just mathematical constructs. There are no fields. There is no gravitational field. There's no electric field. Oh, sure, I have a charge here and I have a charge here, and there's a force. If the two of them are the same charge, there's a force that pushes them apart. But we just make up the concept of a field so that we can pretend that there's some physical causality here. Oh, the field causes this thing to move. The field doesn't cause anything to move. It's a virtual reality. It's all information-based. Our reality is information-based. You see, that force that's pushing them apart isn't caused by the field. The field doesn't cause things. It's just a mathematical, something we make up mathematically. It doesn't cause force. Force is a real thing. You see, so we trick ourselves. That's another thing where we believe these fields are real. Fields aren't real. They're just mathematical constructions. Matter of fact, a very famous physicist, John Wheeler, made the statement, he said early on in his career, he thought that everything was fields. And then he realized that was wrong. Then he thought everything was particles. And then he realized that was wrong. And then he realized everything is information. That's John Wheeler's it from bit. You know, our reality comes from bits, information. So he was a very wise man and probably one of the best physicists of all time. So anyway, that's actually the way it is. They're really, fields are just constructs, and we pretend they're physical things, but they're not. All they do is predict behavior. The field makes the prediction that this charge over here is going to feel a force pushing it away. Okay, but predicting that that force will occur is not the same as creating that force. The field is predictive because it's working the math of which the virtual reality model is using to compute that field, so you can predict it. But making predictions and causing things are different. And that's another place where physicists confuse themselves with the math. They make up the math, then they attribute it to have some physical meaning. Oh, it's a field. And then they start to believe that. See, I can predict when a bus arrives at my street corner, but that doesn't mean I caused the bus to arrive there. There's a difference between predicting and causing. And physics has forgotten that. There are no fields. There are no, magnetic fields, electric fields. There's not even any, what does Rupert have? Morphic fields. There just aren't fields. Fields are mathematical fictions because we want there to be a physical causality, and there isn't one at action and a distance. So we make up the mathematics that predicts what this force will be. We make up the mathematics that predicts what the gravity going to be. When things change, move these masses around, how's the gravity going to change? Well, we have gravitational fields. And then we believe that they're real things, but they're just predictions of results. And they work because that's the way the results are calculated as information. The idea is that virtual reality is information-based reality. And the virtual reality rendering engine has to compute what these things are. Mm-hmm. So the virtual reality rendering engine computes what the force is between these two charges, and that's what you measure at that point. Okay. And if you have that mathematics or something close to it that the rendering engine uses, you can predict what that force is going to be. That's your field equation. That's your electric field. That's your math that's similar to what the rendering engine is using, so you can make accurate predictions. And then you turn around and believe that math actually creates the force. It does not. You see, you just believe that. So in any case, that's the nature of reality. And that's why MBT is not full of math, but that does not make MBT not scientific. You get to be scientific by being logical, not by being full of math.
Well,
That's
thank you.
the
That is really fascinating. And I was understanding this. I know. I hope this puts into perspective um, for all those who ask about whether your theory has math or not. I hope this puts things into perspective.
Mhm.
Um,
Well, you know, quantum mechanics, quantum physics, relativity, all those things are part of the logical consequences of my theory. My theory is above those. My theory is or above, beneath them, if you like, the foundation. You know, above them in sort of the hierarchy of concepts, but beneath them is a foundation. So really, you know, quantum physics and all of the science, that mathematics is really on the tail end of the virtual reality idea. The virtual reality derives that stuff. So quantum math, the math of quantum physics, is derived from virtual reality concepts. Same with relativity. That math, you can derive that out of virtual reality concepts. So the math of my model is there downstream. But I'm not talking about those downstream logical consequences. I'm talking about the foundation, the change in perspective that allows us to understand how to better understand the reality in which we live by answering more of those unanswered questions, by filling in those things that just go unanswered right now. So that's the point. A model isn't decided to be a good model because people like its theory. It's a good model is whether or not it answers questions. You know, how does it perform? What does it explain? That's what makes it a good model.
sure. And your theory also does something quite remarkable in that it bridges quantum mechanics and relativity.
Well, it shows them both being derived out of the same foundation, right? You start with the foundation and it says, well, here's relativity, here's quantum mechanics, and they both connect to the same foundation. So it's the thing from which they both emerge into their own areas. You know, so that yeah, it in that way it is a toe. You know, Einstein's toe was to find the one overarching idea that from which both relativity and quantum mechanics flowed. One overarching concept, and those two were both subsets of that overarching concept. Well, it does that. So that's the little toe, but this is a big toe. So it not only does that, not only, you know, solves Einstein's little toe, but it's the bigger toe because it also describes everything subjective as well as everything objective. So quantum mechanics and relativity are only about the objective world. Most of science is about the objective world. And it's good. That's a good thing to understand. You know, science is a good thing to learn about that objective world. But this model also explains the subjective world. It's also a model of consciousness. Matter of fact, it's fundamentally a model of consciousness. And once you understand the subjective world, you can be just as reliable and just as precise about what's going on there as you can in the objective world. Would you like to know why you are unhappy? Why you get angry? Why your life is a struggle? Would you like to understand how such and such a thing affected you? This is all subjective. You know, why you make the choices you make? Well, this logic of the subjective works just as well in the subjective world as the logic of the objective. So now you have subjective science as well as objective science, and you can understand all of that subjective stuff very accurately and precisely as you can the objective stuff. So that makes it a big toe. It's the theory of everything, including objective, which is, you know, just one piece of it, not even the most important piece. You know, science isn't the big piece, but the subjective, which is us and why we're here and what we're here for, and the quality of our consciousness and what's right and wrong. You know, what's the What about being? What is beingness? What's that? Ontology, cosmology, epistemology, all those things in metaphysics all come out as being answered here with this same foundation. So that's why it's a big toe. It not only answers the unknowns in the objective world, it answers the unknowns in the subjective world. Even theology falls out. So, well, that's it. And that's why I'm not awash in equations, and why I can write a book for, the guy on the street. And it is fundamental physics, and it is science, even good science. It's based on logic. And I think it's a much better model than the one we have now, because it answers more questions. So that's it in a nutshell. It doesn't have to be mathematical to be good science. It just has to be logical. And the math is downstream. It's already downstream, Like I say, relativity, quantum physics is part of downstream for this idea. So the math is already there. I don't have to reproduce that. I just have to derive it, derive the foundation. The rest of it all falls right out.
Thank you, Tom. This has been really, really fascinating. And I think that will put things in quite a good perspective for those who are asking for equations.
Mhm.
Thank you very much.
Tom Campbell here. I and MBT Events hope you liked this video. We now have well over 1,000 hours of free video on this user-friendly, ad-free YouTube channel. Though these videos are free to our viewers, they represent many thousands of hours in production and editing, and many thousands of dollars invested in video and audio equipment, along with the required computers and software to store and process the raw video into finished products. So far, all of this content has been funded directly out of our own pockets. Be assured, we will always continue to do what we can. It's our life, our purpose, a labor of love that we will continue to pursue as best we can. However, those pockets are not as deep as they used to be. Thus, we are now seeking to augment our resources with support from our viewers. If you find something of significant value in our videos, please consider supporting their production through our newly created Patreon account or through a one-time donation. The links are in the description below. Thank you.